Good morning, my dear students. We have been discussing about the molecular orbital theory and its details. We have seen what is molecular orbital theory, what are the postulates of molecular orbital theory, how a molecular orbital picture is constructed, and we have ended electrons to the molecular orbitals and we have calculated the bond order for the molecules. Now our discussion proceeds to the molecular orbital picture of nitrogen molecule and oxygen molecule. We have seen for the case of nitrogen molecule, when we write the molecular orbital, the pi 2py and pi 2px orbitals formed from the 2p orbitals having minimum energy than sigma 2pz. So when we write the molecular orbital configuration of nitrogen, we could say sigma 1s is having minimum energy, then sigma star 1s, then sigma 2s, then sigma star 2s. Then it goes to pi 2px, which is having same energy that of pi 2py. Then we have the sigma 2pz. Moving to the case of oxygen, there is a difference in the configuration. Sigma 2pz have minimum energy than pi 2px and pi 2py. So the energy of sigma 2pz is lower than the energy of pi 2py and pi 2px. That means for oxygen molecule and nitrogen molecule, there is a change in their configuration when we construct molecular orbital picture. Note down the difference between nitrogen and oxygen when we draw the molecular orbital picture. Now consider the case of nitrogen molecule. We know nitrogen atom is having a configuration of 1s2, 2s2 and 2p3. So when two nitrogen atoms combine to form N2 molecule, there is 15 electrons. These 15 electrons has to be accommodated to the molecular orbital of nitrogen molecule. And we know in case of nitrogen molecule, there is a change in configuration in the 2p level. That is, pi 2px and pi 2py have lower energy than sigma 2pz. So when we enter the electrons to the molecular orbital, we have sigma 1s having minimum energy, then sigma star 1s entering second and third electron, third and fourth electron, sigma 2s fifth and sixth electron, sigma star 2s seventh and eighth electron. So the remaining 6 electrons are entering into the pi 2px, pi 2py and sigma 2pz. So when we write the molecular orbital configuration of nitrogen, we could say nitrogen have a change in nitrogen molecule have a change in its configuration at the 2p level. So the molecular orbital configuration becomes Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px is equal to pi 2py and sigma 2pz2. So this is the general configuration of nitrogen molecule. But 1s orbitals are considered as K shell. So sigma 1s and sigma star 1s2 are abbreviated as KK. So when we represent KK, it means there is a sigma 1s2 electron and a sigma star 1s2 electron. So we could say the configuration of nitrogen could be either written as KK, that means sigma 1s and sigma star 1s here finished. Sigma 2s2, sigma star 2s2, pi 2px2 is equal to pi 2py2 and sigma 2pz2. Now we have to calculate the bond order. See, we have 2, 4, 6, 8 and 10 electrons in the bonding molecular orbitals and 2, 4 electrons in the anti-bonding molecular orbital. So substituting the values of number of electrons in the bonding molecular orbital and in the anti-bonding molecular orbital, we get 10 minus 4 by 2, that is equal to 3. This clearly indicates that nitrogen molecule contains a triple bond. N2 molecule is having 3 bonds, 1 sigma and 2 pi bonds. Now see here, all the electrons are paired in the molecular orbitals. Hence, this molecule is diamagnetic. So the bond order value we are getting 3. It clearly shows that between two nitrogen atoms there are 3 bonds. One is a sigma bond and remaining 2 are pi bonds. And all the electrons are paired in the respective molecular orbitals. So we could say nitrogen molecule is diamagnetic in character. Got it? Take down. Now consider the molecule N2 plus. N2 plus is nitrogen molecule from which one electron has lost. N2 molecule contains 7 plus 7, 14 electrons, while N2 plus molecule have 13 electrons only. Why only 13 electrons? Because from nitrogen molecule, 1 electron has lost. So when we write the MO picture of N2 molecule, we could represent. See, the electrons are ended into the orbitals, and in case of sigma 2pz, there is only 1 electron. In case of N2 molecule, there was 2 electrons in sigma 2pz. Now it is N2 plus. Hence, 1 electron has lost from the sigma 2pz. That means sigma 2pz is a bonding molecular orbital. In case of nitrogen molecule, there was 10 electrons in the bonding molecular orbital. But now there is only 9 electrons in the bonding molecular orbital. So we could write the configuration, MO configuration of nitrogen molecule as KK, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, and we have sigma 2pz1. Now there is only 9 electrons in the bonding molecular orbital. Hence the bond order may be 9 minus 4 divided by 2, that is equal to 2.5. In case of nitrogen, the bond order was 3. One electron has lost from the bonding molecular orbital. Hence the bond order of N2 plus is 2.5. This clearly shows that this molecule is paramagnetic to the extent of one unpaired electron. Why? Because in the sigma 2pz there is only one electron. Hence this molecule is paramagnetic. We have seen N2 molecule, that is nitrogen molecule, was diamagnetic because all the orbitals are fulfilled. And the bond order was 3 for N2 molecule, nitrogen molecule. But moving to N2 plus molecule, the bond order is found to be 2.5 and the molecule is paramagnetic. Take down. Now we check the molecular orbital picture of oxygen molecule. Oxygen molecule O2. We know O2 molecule is formed by the combination of two oxygen atoms. Each oxygen atom is having 8 electrons in their atom. They are 1s2, 2s2 and 2p4. But moving towards the molecular orbital picture of oxygen, we know the sigma 2pz orbitals have minimum energy than pi 2pz and pi 2py when we consider the overlapping of 2p orbital. Hence, there is a difference with the configuration of nitrogen. So the minimum energy is to 1s, sigma 1s, then sigma star 1s, then sigma 2s, then sigma star 2s, then sigma 2pz. Then only we have pi 2py and pi 2px. So this change in configuration or change in molecular orbital pattern is observed from oxygen molecule to higher molecules. So up to nitrogen there is a different configuration, and from oxygen to fluorine or higher molecules the configuration is changing in 2p orbital. See here, these electrons are entered into the orbitals. So we know 4 electrons are entered into the sigma 1s and sigma star 1s, which is beneath here. Then another 4 electrons are entering into sigma 2s and sigma star 2s. Now 2 electrons are entering into sigma 2pz, then 2 electrons in pi 2px and pi 2py. Finally, the remaining 2 electrons are entered into pi star 2px and pi star 2py, which have same energy. So 2 electrons are entered equally in 2 different orbitals, pi star 2px and pi star 2py, obeying Hund's rule of maximum multiplicity. Hence, the molecular orbital configuration of oxygen. Now see here, the configuration of oxygen molecule could be represented like this one. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2. Then pi 2px2 is equal to pi 2py2. Then pi star 2px1 and pi star 2py1. So instead of sigma 1s and sigma star 1s, we could represent as kk. Now we have to calculate the bond order of this particular molecule. We know we have 2, 4, 6, 8 and 10 electrons in the bonding molecular orbitals. So 10 electrons are present in the bonding molecular orbital, while 2, 4, 5, 6. 6 electrons are present in the anti-bonding molecular orbital. So 10 bonding molecular electrons and 6 anti-bonding molecular electrons. So their difference by 2 will give you a bond order of 2. The bond order is 2. This clearly shows that oxygen molecule contains a double bond. One is a sigma bond and another is a pi bond. Now see here, when we observe the configuration of oxygen molecule, it is observed that pi 2px and pi 2py have one unpaired electron each. Hence, oxygen molecule is paramagnetic in character. Experimentally, it has proved oxygen molecule is paramagnetic to the extent of 2 electrons. So we could say the bond order of oxygen is 2 and there exist 2 bonds. One is a sigma and one is a pi between oxygen atom in oxygen molecule, and the molecule. Now we take the example of O2 plus molecule. What is O2 plus molecule? From oxygen molecule, one electron has lost. So naturally, that electron has to be lost from the pi star 2py orbital, because electrons will be lost from the last orbital. Here the last orbital is pi star 2py or pi star 2px. So one electron is lost from the pi star 2py. So when we write the molecular orbital configuration of O2 plus, we could say it is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2pz2 x2 is equal to pi 2py2 and pi star 2px1 or pi star 2py1. So one electron has lost from the antibonding molecular orbital. So this is the molecular orbital picture of O2 plus molecule. Calculating the bond order for O2 molecule, O2 plus molecule. We have 10 electrons in the bonding molecular orbital and 5 electrons in the anti-bonding molecular orbital. See, this 2 plus 2 plus 1. Only 5 electrons in the anti-bonding molecular orbital. So 10 minus 5 by 2 is equal to 2.5. That means for O2 plus molecule, the bond order is greater than oxygen. Why? Because for oxygen the bond order was 2, while for O2 plus the bond order is 2.5. Hence we could say O2 plus molecule is more stable than oxygen molecule. Take down. Now we consider the molecular orbital picture of O2 minus molecule. O2 minus molecule. That means one electron is added to oxygen molecule. Oxygen molecule contains 16 electrons while O2 minus molecule contains 17 electrons. So the MO picture is here: sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2py is equal to pi 2px2. Now see here, the addition electron is entering into the pi star 2py orbital. That means the addition electron has entered into the anti-bonding molecular orbital. Anti-bonding orbital of pi star 2py. Got it? Take down. See here, the MO electronic configuration I have written, and calculating the bond order for O2 minus, the bond order is 1.5. That means O2 minus molecule is less stable than oxygen molecule, O2 molecule. Why? Because for O2 molecule the bond order was 2 and O2 minus molecule the bond order is 1.5. So when we consider O2, O2 plus and O2 minus, which is more stable? O2 plus is more stable because its bond order is 2.5, while O2 minus is least stable because its bond order is 1.5. So bond order will give you the idea about the stability of the molecule. Take down. Now we discuss about the molecular orbital diagram of heterodiatomic molecule. First we take the example carbon monoxide. When we consider carbon monoxide, one molecule of carbon monoxide is made up of one carbon atom and one oxygen atom. Carbon atom contains 6 electrons and oxygen atom contains 8 electrons. So total there is 14 electrons. And we know carbon combines with oxygen to form carbon monoxide. Oxygen is more electronegative than carbon. There are different approaches to explain the molecular orbital picture of carbon. Now we are seeing the basic preliminary concept of the molecular orbital diagram of carbon monoxide. So carbon is having a 1s2 configuration. Similarly, oxygen is having a 1s2 configuration. So 1s orbital of carbon combined with 1s orbital of oxygen to form sigma 1s and sigma star 1s. And that electrons will be entered into the sigma 1s and sigma star 1s orbitals. Now moving to higher orbitals, see here, the energy of oxygen, the atomic orbital, the energy of atomic orbital of oxygen is represented down than the energy of atomic orbitals of carbon, because oxygen is more electronegative than carbon. When we draw the MO picture of carbon monoxide, we have to represent the atomic orbitals of oxygen bit below than the atomic orbitals of carbon. So the 2s orbital combine with the 2s orbital of oxygen atom to form sigma 2s and sigma star 2s. Moving towards the p orbitals, oxygen is having 4 electrons in the p orbital, while carbon is having 2 electrons in the p orbital. So these p orbitals will combine to form sigma 2pz, pi 2px and pi 2py, pi star 2py and pi star 2px, and finally sigma star 2pz. We have total 14 electrons. These electrons are endowed into the orbital. 2 electron to sigma 1s, another 2 electron to sigma star 1s, then 2 electron to sigma 2s, another 2 electron to sigma star 2s, next 2 electron to sigma 2p z2, then pi 2px and pi 2py. So only 4 electrons are present in the anti-bonding molecular orbital, while 10 electrons are present in the bonding molecular orbital. Hence, the configuration of carbon monoxide become Kk, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2 is equal to pi 2py2. And the bond order is found to be 3. This clearly shows that between carbon and oxygen there is 3 bonds existing. 3 bonds are existing. There are different approaches for explaining the molecular orbital picture of carbon monoxide. But you try to understand this basic concept. When you come to final degree, we have a Coulson approach that is entirely different. Now you listen to this concept of carbon monoxide. We have seen the molecular orbit of carbon monoxide. But to explain certain observed phenomena, modification to the molecular orbital picture is needed, especially for diatomic heteroatomic molecule. For example, if I take CO and CO plus, carbon monoxide and CO plus. CO plus is carbon monoxide from which an electron has lost. Their bond length were observed to be 112.8 for carbon monoxide and 111.5 for CO plus. That means for CO plus, the bond length is lower than the bond length of carbon monoxide. You got it? CO plus have lower bond length than CO. Got it? Just to think, when the bond length decreases, naturally bond order increases. Or we could say, when the bond order increases, the atoms are closely packed, hence the bond length decreases. Now, if we take CO and CO plus, CO and CO plus, see here, if this is the MO picture, when CO becomes CO plus, one electron has to be lost from the bonding molecular orbital. This is the bonding molecular orbital. If electron is lost from the bonding molecular orbital, naturally the bond order decreases. When bond order decreases, what happens? Bond length increases. But for CO plus, the bond length is decreasing. That means the electron has to be lost from the anti-bonding molecular orbital rather than bonding molecular orbital. You got it? Think carefully. Bond order increases, bond length decreases. If CO plus should have lower bond length, that means the bond order of CO plus should be lower than the bond order of CO plus. You got it? Or we could say the bond order of CO plus is greater than the bond length of CO. Don't get confused. Bond order is inversely proportional to bond length. That you got it? Bond order is inversely proportional to bond length. As the bond length increases, bond order decreases. If the bond order decreases, here the electron has to be lost from the antibonding orbital. Okay? So, this configuration has to be changed. That means this is the MO, modified MO picture. See here, this is sigma 1s, this is sigma star 1s. This is sigma 2s. And the antibonding sigma 2s orbital is having higher energy than the corresponding sigma 2pz. So the MO configuration of carbon monoxide is totally changed. Totally changed. Now you see here, look carefully. The electron, last electron is losing from sigma star 2s, which is a anti-bonding orbital. When electron is lost from anti-bonding orbital, naturally the bond order decreases. Because bond order is equal to number of electrons in the bonding molecular orbital minus number of electrons in the anti-bonding molecular orbital divided by 2. So, to explain this phenomenon, we have to change the molecular orbital configuration to sigma 1s, sigma star 1s, sigma 2s, pi 2px2, pi 2py2, sigma 2pz2, and finally sigma star 2s2. This is an important question of JAM examination. So, to explain this phenomenon, we have to think about this molecular orbital configuration. You got it? You got confused? If you have any confusion, we will discuss later. But just you write, bond order is inversely proportional to bond length. Then you just think, so you get the answer. Okay? Now I am taking the case of nitrogen oxide, NO molecule. So I am not explaining anything. Just I have shown you. This is the atomic orbitals of nitrogen and oxygen. The atomic orbital of oxygen is having lower energy than nitrogen. Electrons will be ended. Total there will be 15 electrons. And this is the configuration. And the bond order becomes 2.5. I am not explaining anything here. Just take down. Very similar. Now the question is, NO molecule is paramagnetic. True or false? NO molecule is paramagnetic. It is true. Why? Because there is a one unpaired electron in the pi star 2py. So this molecule is paramagnetic and the bond order is 2.5. Now we consider the molecular orbital arrangement of HF, hydrogen fluoride. In hydrogen fluoride, we have hydrogen and fluorine. Hydrogen is having a 1s1 configuration while fluorine is having 1s2, 2s2, 2px2, 2py2 and 2pz1 configuration. It has observed that the 1s orbital of hydrogen combines with the 2pz orbital of fluorine to form sigma orbital which has sp and sigma star sp orbital. That means the 2s and 1s orbital of fluorine remains as such. Only the 2pz orbital of fluorine combines with the 1s orbital of hydrogen to form a sigma sp hybrid orbital and a sigma star sp hybrid orbital. All the other electrons in the orbitals remain as non-bonding molecular orbital. You got it? All the other orbitals, that is 1s, 2s, 2px and 2py, they all remain as non-bonding molecular orbitals predominantly with fluorine character. Only the 1s orbital of hydrogen overlap with the 2pz orbital of fluorine because they have only the same symmetry around the internuclear axis and same energy. So now total 2 electrons are there. 1s electron of hydrogen and 2pz electron of fluorine. They enter into the sigma sp orbital. So the molecular orbital configuration is sigma sp2. All the other orbitals remain unhybridized, non-bonding molecular orbitals. Hence, the bond order will be 2 minus 0 by 2 is equal to 1. So we could say HF is a special molecule in which the 1s orbital of hydrogen overlap with the 2pz orbital of fluorine to form sigma sp bonding molecular orbital and sigma star sp anti-bonding molecular orbital. All other orbitals of fluorine remains as non-bonding molecular orbital. So a new term has coming, non-bonding molecular orbital. We have seen bonding molecular orbital and anti-bonding molecular orbital. Now a new term has come, that is non-bonding molecular orbital. Got it? Take down. So thank you my dear students, and we have finished that module, that is the first part of chemical bonding, and we will conduct an examination later. I will tell you the date later. So go through the notes in the module, check the answers, prepare the questions and be prepared for the examination. See you next week. Thank you. Thank you very much.